And I will be presenting my answers for all the three questions that has been given. To begin with, my presentation is based on this paper for near crack-free additive manufacturing of novel tungsten, niobium, and carbon alloy. My presentation is primarily split up into three parts, and so well, this video would be to keep a track of the time. The first part being the optimization and the composition for the higher niobium content, and second part being the oxygen segregation and embrittlement, and the third part being the non-increment solidification modeling, and the last part being the conclusion and the summary. To begin with, the main objective of this paper, this answer would be to maintain the crack healing mechanism for the higher niobium content and to ensure that liquid phase availability at the later stages when to enable crack backfilling and to prevent any sort of hot tears during the terminal stage of solidification. I'll be considering several thermodynamic indicators in the pseudo-binary phase diagram and in the Shell-Gulliver simulations. Their influences and the parameters have been discussed as follows. The first part being the split fraction and the onset of the eutectic reaction, which is primarily the phase when the time when the liquid phase starts transforming into the BCC plus FCC carbide phase. And this primarily governs the crack healing liquid becomes available. This For effective crack healing, the liquid must be precisely present when the dendritic networks get formed during the higher FS value, primarily near to more than 0.65. If it starts at very early phase, then it becomes it's completely absent when it's absolutely necessary when the tensile stresses peak, and this makes it completely ineffective. The second point being the dendritic coherency point, the relationship lies in between the FS value for the eutectic phase and the FS value for the dendritic coherency point. This primarily comes into play when the dendrites form solid networks and tensile stresses starts to peak at their contact points. So if we have the Fs value or the solid fraction value for eutectic case larger than that of the dendritic coherency point, it ensures that even after the solid skeletons forms, the liquid is available. The liquid remains to permeate and relax the stresses, preventing initiation of any sort of hot tears. The the third and the fourth part includes the temperature range and the slope of the eutectic plateau. This parameter primarily governs the duration and the effectiveness of the crack healing process. A wide temperature range provides a larger window at the maximum time for the eutectic reaction to complete itself. This ensures that the maximum time is available for the liquid to backfill to ensure grain bridging and the backfilling, which for sealing cracks permanently at the most vulnerable terminal stage of solidification. It is primarily necessary that uh, a shallow slope is observed near Fs equals to 1. A steeper slope indicates a rapid solidification, while a shallow slope allows maximum time for the liquid to backfill and to relax the stresses. So these are the primary parameters I will be focusing on. The work summary has been provided as follows, which will be the primary concern during this entire optimization process for the higher niobium content of 15%. Thank you, and I'll be moving on next to the second part. The objective includes quantifying oxygen segregation tendency and embrittlement effect at the critical interface using the first principle methods. My primary method includes density functional theory. My software is VASP. My pseudo potential is projector augmented wave. My functional is PB exchange correlational functional. My target interface includes the tungsten rich solid solutions and the niobium carbide interface boundary. To move on to my next part and my workflow, it includes preparation of the bulk unit cell, which I prefer using atomic simulation environment to create to, which I usually do in my work so far in material science. Using ASC, I can create the bulk unit cells. I prefer using Vesta to create the surface labs. We need to look for matching the surfaces. So being tungsten being the BCC and niobium carbide being the FCC, 100 is the preferred low energy surface of contact. We need to stack them up at a point. So this is the preferred direction. Next, moving on to optimizing the surfaces, but we also, after optimizing individual slabs, we also need to look into the optimized lattice constants to check for the misfit strain, which is nothing but the relative change in between these two optimized lattice constants, and the misfit strain should not be greater than 2 to 3%. It always has to be less than that. After this optimization and the misfit strain checking, we need to look for creating the final supercell, which we do by removing the vacuum layer in between and stacking these layers one after the other of tungsten and the niobium carbide. While stacking up, we need to have this intermediate distance being equal to the atomic radii, which we eventually optimize for the lowest energy atomic positions using VASP as well. After the optimization is done, we have the energy of the interface in hand. We need to also do for that with interface along with oxygen as well.
We choose a desired lattice site and place an oxygen out there. I prefer doing this using similar to what I did initially using atomic simulation environment. Using AAC, we can place that oxygen out there for that in that desired lattice site and optimize that as well, following the same procedure as we did for the interface. We have the final energies in the outcar file, and then we optimize oxygen as well, and it's more like optimizing an oxygen in a box. So after we have the optimized structure, we have the final energy from the outcar. We multiply with a factor of half to have the final energy. We put all of them in this formula for calculation of segregation energy and have the ultimate value. A negative value indicates a favorable segregation. Moving on to the calculation of the work of separation, since we have the optimized slabs from the initial cases, so we have the energy for that. We have the energy for the interface as well, and we also have the energy for the interface along with oxygen. We also need to keep a check while making these structures using AC or while cutting them using the Vesta, that the areas remain the same for the sake of calculation. Finally, we have the final work of separation values for both clean and oxygen along with oxygen. A case where the work of separation for clean surface, clean interface larger than that with oxygen ensures a strong, tough interface, while a large reduction indicates a severe embrittlement effect. Moving on to my validation and databases, I have used VAS with projector augmented wave potentials. Materials project becomes a great source for the postcards. We can have the validation from the X-ray photoelectron spectroscopy data and also from the literature of scanning electron microscope fractography as well. Thank you. Moving on to my next answer, the final one. Is that extreme cooling rates of 10 to the power 5 to 20 to the power 7 kelvins per second in laser power bed fusion push the alloy far from equilibrium. This poses certain challenges. The extreme cooling rates cause severe microsegregation, solute trapping, metastable phase formation, and retained supersaturation. The limitation or this to accurately model phase evolution under these conditions, the calculation of phase diagrams or the CalFAD must be coupled with the kinetic models. The hierarchical computational framework can be stated as follows: the DICTRA simulations or the diffusion control transformations. This is the most direct method coupling calculation of phase diagram thermodynamic database with a database of atomic mobilities. The inputs include the alloy composition, thermodynamic and mobility database, and imposed cooling rates. We get as of outputs as the fractions, phase fractions versus time, composition profiles, prediction of solute trapping, and the degree of supersaturation in the primary phase. The effective non-equilibrium solidus temperature. What role does it play? We can say that provides the quantitative data on how elements like niobium and carbon are distributed during the rapid solidification, which dictates the volume fraction and the composition of the subsequent eutectic phases. The second comes into the phase field modeling. The DAYS method simulates the evolution of microstructure morphology itself using calculation of phase diagram data for local thermodynamic driving forces. The inputs include the thermodynamic or kinetic data from CalFed or DICTRA, interface properties of cooling rate. The outputs being the visual and the quantity prediction of the dendritic morphology and the eutectic structure. Identification of the metastable phases that may form due to the kinetic suppression of the equilibrium phases. What it does is it directly predicts the heterogeneous microstructure observed in the paper, linking process conditions to the microstructural features like segregation channels. The last one being the advanced shell model. It is an analytical model that modifies the classical shell model to account for the finite diffusion of the solid. What it does is a quick microsegregation estimate and helps as a screening tool as well. Moving on to my next part, which is the heat treatment design guidance. For the heat treatment design and guidance, what it does is the homogenization treatment. The microsegregation profiles from the DICTRA serve as the initial state. DICTRA can then simulate an annealing process to predict the time and temperature required to have a homogeneous composition, optimizing the treatment to minimize energy use and prevent grain growth. Precipitation hardening includes if the model predicts a supersaturated solid solutions under laser power bed fusion or the calculation of phase diagram that can be used to calculate the time temperature transformation diagrams. This guides the design of an aging treatment to precipitate fine, strengthening carbides in a controlled manner, enhancing the alloy strength. That's all. These are all my answers for all the three questions that I have so far.